In this video, we're going to prove some trig identities. However, before we can do that, we have to sort of have the list of trig identities that you've already proven in class. So I'm going to, this will be on the website, but just to kind of go through it quickly, we have the Pythagorean theorem, we have the tan, and then we have a bunch of identities for sine and cosine. Then we have angle sum and double angle. And of course, the double angle fall out from the angle sum. You prove that in class. So these are the ones, the basic ones that we want to keep in mind whenever it is that we're being asked to prove trig identities. And I'm going to do 4 examples here of proving trig identities. The first one is that we're going to prove that cosine of 2 alpha equals 1 minus 2 sine squared alpha. And the deal with proving trig identities is that you are allowed to do work on either side of the equation. So I could simplify the cosine 2 alpha, or I could simplify the 1 minus 2 sine squared alpha. However, I cannot do anything the same to both sides. I'm not solving anything. So I can't add 4 to both sides, divide by 2, take the sine inverse on both sides. Nothing can be done to both sides. I may only act on one side alone using my identities. So what I'm going to do here is I'm going to say, well, I have an identity for a double angle for 2 alpha. So I'm going to rewrite cosine 2 alpha as cosine squared alpha minus sine squared alpha. And then I actually know a relationship between cosine squareds and sine squareds. So I'm just going to remind myself that that is the Pythagorean theorem identity, sine squared alpha plus cosine squared alpha equals 1. And I can see that I really want to have only sines. So I'm going to replace my cosine, which means I need to solve this equation for cosine. So when I solve it for cosine, I get 1 minus sine squared alpha. So I'm now going to replace the cosine squared alpha with 1 minus sine squared alpha. I still have the sine squared alpha. And lo and behold, I now have 2 sine squared alpha. Now, I happen to work all of this out on the left-hand side. You could have also done some simplifying on the right-hand side, but again, you'll notice that I didn't do the same thing to both sides. At no point in time did I add something to both sides or multiply something on both sides. They are 2 separate entities that I'm trying to get to look the same. Our second example, prove that cosine 2 alpha equals 2 cosine squared alpha minus 1. So again, I'm going to use the fact that I know the double angle. I know the double angle for cosine is cosine squared alpha minus sine squared alpha. And I know again this identity up here, the Pythagorean identity. And so I could have solved this equation. So I know I want to get cosines only. So I'm going to solve that equation for sine squared. So when I solve it for sine squared, I get 1 minus cosine squared alpha. So now I'm going to replace the sine squared, so I still have cosine squared alpha, minus, and I'm going to replace it with 1 minus cosine squared alpha. I then distribute my negative, and then I have 1 cosine squared and another cosine squared, which gives me 2 cosine squared minus 1, which is what I was looking for. And again, I only worked on the left-hand side in this problem, but that isn't necessary. You could also work on the right-hand side, as long as you don't do the same thing to both sides. You're not solving, you're only working on one side to get it to look like the other side. Our next example is a little longer. We are going to prove that 1 minus 2 cosine squared x equals tan squared x minus 1 all over tan squared x plus 1. In this case, interestingly enough, I am actually going to work on the right-hand side. I'm going to see what I can do about these tans, because I know that tans can be written as sines and cosines. So I'm going to rewrite this tan squared as sine squared over cosine squared, still minus 1, all over sine squared over cosine squared plus 1. Okay, I'm going to play with this a little bit more. You know, I'm looking at this and I'm like, well, you know, these fractions are complex fractions. Let's get common denominators for both of these fractions. So I've got sine squared x minus cosine squared x all over cosine squared x. And on the bottom, I've got sine squared x plus cosine squared x all over cosine squared x. See this negative cosine squared over cosine squared? That's my negative 1. And my cosine squared over cosine squared, that's my positive 1. That I've simply rewritten this 1 as a 1 that has the same top and the bottom. And now I can simplify these fractions because if we remember, when I divide fractions, it really is multiplication of the reciprocal. Oops. And so when I do that, I have sine squared x minus cosine squared x all over cosine squared x times cosine squared x all over sine squared x plus cosine squared x. And so multiplying these, I can see that my cosine squared x's cancel, and I'm left with sine squared x minus cosine squared x all over sine squared x plus cosine squared x. But I actually know that sine squared x plus cosine squared x, that's my identity for my Pythagorean theorem identity. And so I can actually simplify that to 1. Which means I am now in the place where I simply have sine squared x minus cosine squared x. Well, again, I've got that lovely, I know that I want to get cosine squared, so it'd be great to get rid of the sine squared. And in our previous problem, we did that. We simplified sine squared to be 1 minus cosine squared. So I'm going to do that again. I'm going to replace my sine with 1 minus cosine squared. Still have my minus cosine squared. And then that gives me 1 minus cosine squared, 2 cosine squared x, which is exactly what I was trying to get. Now, the nice thing about proving these identities is there actually can be many ways to do it. This happens to be the way that I saw proving 1 minus 2 cosine squared x equaled tan squared x minus 1 over tan squared x plus 1. But that doesn't mean it's the only way to do it. It's simply the process of getting to the place where the right-hand side and the left-hand side look the same. Our last example is to prove that 1 over tan x plus tan x equals 1 over sine x cosine x. So again, there are lots of ways to do this. I am actually going to work on the left-hand side this time. So I'm going to replace tan with sine over cosine. And I'm going to replace tan with sine over cosine. I know that when I'm dividing fractions, I'm multiplying by the reciprocal. So this turns into cosine x over sine x. And this is looking more and more like what I want, and especially since if I'm going to add 2 fractions, I need a common denominator, and lo and behold, the common denominator is the denominator I want in the end. So I end up by multiplying the first fraction by sine x over sine x, and the second by cosine x over cosine x, which is going to get me, oh, I'm sorry, I did that exactly backwards. wanted it exactly the other way. Multiply the first fraction by cosine x over cosine x, and the second by sine x over sine x. So in my numerator, I get cosine squared. And in my numerator for the second fraction, I get sine squared. And my denominator is sine x cosine x. Well, this is really nice because now I have my Pythagorean theorem identities. So I have 1 over sine x cosine x. And that equals exactly what I was looking for it to equal. Again, many ways to do these problems. You get to play around and decide how it is that you want to do them. You could have changed this into 2 fractions. You could have done a whole variety of things. It's just a matter of getting the left-hand side and the right-hand side to look the same.